next, and she's going to continue telling us about homotopy theory and arithmetic geometry.
Well, thank you very much. So yesterday, we talked about the étale homotopy type. And that associated to a scheme X, a prospace. So in pro-simplicial sets, which we were calling pro-S. And remember what it meant for X to be over ring K. So X is said to be over K if the coefficients of the polynomials underlying X are in K, and if we're only concerned, so coefficients of associated polynomial equations that we're trying to solve, are in K, and if we're only interested in solutions, in rings which contain K or which have a map from K into them. So the solutions, we were denoting X of now R, where K is sitting inside R. And more precisely, this is a map from X to the scheme determined by this is a K. We had some properties. So for X over C, the étale homotopy type was equivalent to a profinite completion, or the profinite completion of the C points with its analytic topology. If we look at spec K for K of field, then the étale covers that we were using to define the étale homotopy type are disjoint unions of spectra of separable field extensions. And since those can always be dominated by Galois field extensions, what you can show is that the étale homotopy type is equivalent to the classifying space of the absolute Galois group. Let's denote that GK. So GK is the Galois group of the separable closure of all the automorphisms of the separable closure of K, which fix K. So in particular, if we're interested in homotopy classes of maps from étale of spec K to étale of spec L, well, this is a map between classifying spaces of inverse limits of discrete groups. And so in particular, we get, if these maps were pointed, we would get an induced map on Galois groups. Since they're not pointed, that's an induced homomorphism up to conjugating by GL. So we have a map like this, which is a bijection. And furthermore, the topology is worked into the system. So what the homotopy classes of maps are between the étale homotopy types are continuous group homomorphisms between the absolute Galois groups taken up to conjugating by some element of the Galois group of L. So we divide out by the equivalence relationship where two homomorphisms are the same if they differ by conjugating by an element of GL. So some other properties are, let's say, X, a finite type over K. We could form X K bar, which is what happens when we only consider the solutions and extensions of K bar, or equivalently, the base change, fiber product, to K bar. And then under mild hypotheses, which I hope are only finite type, we get that we have a fiber sequence from the étale of X K bar to étale of X to the étale homotopy type of spec K. And that may be the list of properties we're going to see, except there's one more thing that let's get notation for. So Grothendieck was very interested in pi 1, and he had another way of thinking about the pi 1 of the étale homotopy type. So we could take pi 1 of the étale of X, and when X is sufficiently nice, let's say normal, smooth suffices, then this is the same as something else that Grothendieck considered in SGA1. So let's call, we'll restrict ourselves to normal schemes, so X normal. Then we have that pi 1 of the étale homotopy type is the same as an SGA1 defined, or étale pi 1, and we'll call those both pi 1 of X. Okay. So we have étale homotopy type. We're going to use this to try to make progress towards finding solutions to polynomial equations. And the particular way we'll think about that right now is via Grothendieck's and abelian conjectures. We'll start with a question. Let's take rational numbers. So we'll take A, B in Q star. And we'll look at the absolute Galois group of the extension you get by adjoining the square root of A to Q. And similarly for B. So choose and ask when is there an isomorphism between the absolute Galois group of Q adjoin the square root of A and Q adjoin the square root of B. And the answer is lovely. It's if and only if these fields are actually the same. So if and only if Q adjoin the square root of A is itself isomorphic to Q adjoin the square root of B. And if we wanted to take it all the way back down to how to choose elements in Q star, this is if and only if A is equal to B in Q star over Q star squared. So if we compare with how we get maps between étale homotopy types, these are just the maps between the absolute Galois groups. So we get to conclude that in this case, the isomorphisms of schemes, spec K to spec L, are the same as the natural map is an equality. The isomorphisms in the homotopy category of the étale homotopy types. Well, here, this is Q adjoin the square root of A, and the second field was Q adjoin the square root of B. So this again, spec Q adjoin the square root of A, mapping to the étale homotopy type, spec Q adjoin the square root of B. This is a theorem of Nitric and Uchida, and it says this happens whenever the fields in question are finite dimensional over Q. So there's a theorem of Nitric and Uchida, which says that for K and L finite extensions of Q, the maps from K to L are, or the isomorphisms from K to L are in canonical bijection with the isomorphisms of continuous outer homomorphisms from GK to GL. So the conclusion would hold not just for Q adjoin square root of A, but finite field extensions of Q. And Grothendieck's and abelian conjectures predict a large family of schemes that that are controlled by their étale fundamental groups. So we have a conjecture we'll fix a finite extension of Q. This is called a number field. So for K, a number field, there's predicted to be a full subcategory called anabelian schemes. So there is a full subcategory and K of schemes over K. And this category includes things that look like they're going to have this property, and we're certainly not going to have this property well, I guess that's not certain. That we want to have this property, and this property is in Grothendieck's setup. This property was viewed as a property about pi 1. So we're going to replace the étale fundamental group with the SGA1. We're going to replace the étale homotopy type here with the étale fundamental group from SGA1, and only consider when isomorphisms of schemes are isomorphisms just of the fundamental groups. Like here, G, the absolute Galois group of Q adjoin the square root of B is the fundamental group, because we have that the étale homotopy type of spec K was B of this. So for Grothendieck's and abelian conjectures, the asking whether the étale homotopy types control the maps of schemes gets changed into the double question, what schemes look like B of their étale fundamental group, and when does the étale fundamental group control the scheme? So this subcategory is going to contain things that look like they should be k pi 1s. So part of this conjecture is such that an k has objects. So an k includes hyperbolic curves, so curves, smooth curves with negative Euler characteristic, so with Euler characteristic less than 0, spec k itself, and total spaces of fibrations where the base and fiber are in these anabelian schemes. So we just checked that spec k, when we take its étale homotopy type, it's a k pi 1. If we take fibrations of k pi 1s, they're k pi 1s. Hyperbolic curves are k pi 1s. So far in this partial statement, what we have is the claim that there's a full subcategory of schemes over k. It's containing things that look like k pi 1s. And then the prediction is, so nk is such that, having the property, so that for all x1 and x2 in anabelian schemes over k, the scheme morphisms are the same as the morphisms of étale homotopy types, but in this context, that's morphisms of étale fundamental groups. And then there's some caveats, so such that the morphisms of schemes from x1 to x2 are the same, are a natural bijection with the morphisms of the étale fundamental groups. We're calling this pi 1 of x1 to pi 1 of x2. This is incorrect as stated, and to deal with those things, we'll break it up. For this statement, let's consider dominant maps of schemes. So what this means is that the image is dense. So these are dominant maps. Or maps with a dense image. And over here, the morphisms have to be continuous still, but expressing the fact that these have dense image, the corresponding condition is that the maps are open as well as continuous. So there's one part of the anabelian conjectures, and we'll express this equality, this bijection, as a bijection star. So this is true. Yeah, and note that it's well, it's just a full subcategory. So this is saying that morphisms between schemes, solving the polynomials that are involved in making this set for the listed schemes here is the maps of pi 1. So he's leaving open that there could be even more schemes in anabelian over k, but this is already a strong statement because we have things that are labeled as anabelian. So we have hyperbolic curves. This is saying any two maps, any maps between two hyperbolic curves are the same as maps between their fundamental groups.
Can I ask you to put that board up?
Thanks. So this is true, and even with a little bit more. So any map to a k-pi1 topologically would have that property. And these are morphisms over k. This is in schemes over k. And so these morphisms are also over gk. So in interest of being precise, let's write that down. So these are schemes over k, which means all of our schemes come with a map to k, and we want our morphisms to preserve that map. And then when we take the étale topological type, we'll still have the corresponding commutative diagram. So these morphisms are over gk. And again, since we're not taking based maps, we have this dividing out by the outer automorphisms again. So this is true. And Mochizuki shows for k a subfield of a finitely generated extension of QP, which gets the name subpietic. And x1 smooth, but it doesn't have to be one of these k-pi1s. X2 hyperbolic curve. So curve, smooth curve. Again over k with negative Euler characteristic. Then that bijection holds. Okay, so that's some evidence for the Anabelian conjectures. And this piece, the piece consisting of maps which are dominant, it doesn't pick up the solutions in Q or the solutions in K, because if you had a single solution, a map from spec Q to X, that will never be dominant to a curve. That's just a single point. So we're missing here the original solutions to polynomial equations we were interested in. So let's state the section conjecture. And so this tells us what the solutions to the polynomials are expected to be. So let X be a smooth curve of genus greater than or equal to 2 and compact over K. The compactness isn't necessary, but the statement gets more complicated. So compactness is not a necessary hypothesis. So then the natural map from xk to the homotopy classes of maps in the over category of spec k, but let's leave that off the notation. So from étale of spec k to étale of x, that this natural map is a bijection. So now we've stated all the Anabelian conjectures, modulo the fix for compactness. And let's give some things that are known about them. So the section conjecture is open. But if you so there do exist, there is known to exist curves x such that both sides are empty, so such that of negative Euler characteristic, and these are compact too. So there exist curves, as in the statement of the section conjecture, such that xk is empty, as well as the homotopy class of maps in the pointed category. So there is no map in the pointed category. These are, so that this is empty too. A tall of spec k to a tall of x is also empty, and you could say, well, I'll send everything to a point, but this is inside a category of prospaces mapping to the tall homotopy type of spec k. So we're in schemes over k, which means we have structure morphisms down to spec k. So if we took a diagram like this, and we apply the étale topological type to it, we get a diagram like this. So in particular, this is bad notation, confusing shorthand for maps that fit into this triangle. So they have to respect a map down to spec k. So this means these maps are sections of the map from the étale homotopy type of x down to spec k. Is that clear? Pardon? Yes. Thanks. Yeah, so they are both empty, so that the section conjecture holds. Thanks a lot. So I'm feeling very tongue-tied, and like I just said something confusing. And since it isn't confusing mathematically, let me try again, or give me a sign that this has been expressed clearly. So we have a statement of this section conjecture which tells us what the solutions to polynomial equations are. They're the same as maps of étale homotopy types. But let's be precise about what clear conditions the maps of étale homotopy types have to satisfy. So we started in a category of schemes admitting a map to spec k. So if we apply a tall homotopy type, we get maps to a tall of spec k. So all of our morphisms are definitely respecting a map down to a tall of spec k. So this is poor notation, but it's homotopy classes of maps in a category whose morphisms look like this. And so it could be possible that there weren't any, as in there were no sections of this map. How are we? Okay, so sorry about that. In particular, the section conjecture is true. So i.e., section conjecture is true for these examples for such x. So there are explicitly constructed examples due to Jakob Stix and Harari Samueli with Flynn and there's some other, and Wittenberg. So there are some curves for which the section conjecture holds. Yes?
Should I think of the section conjecture as lift from pi 1
They're just about the same. These are both k pi 1s. So we could have written this in terms of pi 1. And that's the way Grothendieck wrote it. The reason that it's written differently on these two boards is because I couldn't decide which was more clear. And so this is the same thing as homomorphisms over GK, again, because it's over B of GK. And since these are both k pi 1s in prospaces, of homomorphisms from pi 1 of this, which is GK, to pi 1 of X. And there's, again, the fact that these aren't based maps, so all of them get that action. Thank you. All right. So the section conjecture also just behaves well with respect to finite covering spaces. So let's abbreviate this with SC, and then say that SC behaves well for finite étale covering spaces. So if it's true for X, so if section conjecture holds for X and we have and Y maps to X as a finite covering space, finite étale covers is another name for finite covering space. So this is a finite covering space. So then the section conjecture holds for Y. So a really lovely piece of work on the section conjecture is actually in model theory, as in the kind of model theory that's going on in the twin program. But let's write that down. So as in Anna Marie's question, this set of homotopy classes of maps is group theoretically this modification of just group homomorphisms from the absolute Galois group to pi 1. If we replace pi 1 with the absolute Galois group of all the rational functions on X, of all the quotients of the polynomial functions on X, we could make another version. So one can replace pi 1 of X with the Galois group of the rational functions on X and state what's called a birational section conjecture. And it's very similar to saying the section conjecture holds when you pass to smaller and smaller Zariski opens. And for QP and finite extensions of QP, this is true by model theory. So Königsmann showed birational extension, birational section conjecture for finite extensions of QP. And there's other great work on the section conjecture, but I think that's the list, except I also wanted to give reference to Jakob Stix's book. So there's a book by Jakob Stix called Evidence for the section conjecture, which has a lot of nice results on what's known. So let's talk about the relationship of the section conjecture to Sullivan's conjecture on fixed points and homotopy fixed points. So relationship to Sullivan's conjecture. Let's look at this side, and as we did over up there, let's unwind the fact that it's in a category living over a tall of spec k. We have the étale homotopy type for a hyperbolic curve. So we're going to fix a number field and x a hyperbolic curve. Smooth. It can be shown that the étale homotopy type of X is really the classifying space of its étale fundamental group, and that that's also equal to what you get by taking homotopy orbits of the étale homotopy type of the base change to xk bar. So since X was a scheme over spec K, we have a map to the étale topological type of spec K. If we had a section here, we could pull this back. So given phi section, we could pull this back. So this is the classifying space of GK, and we could pull this back to EGK. To a section of the pullback. So phi prime would determine an equivariant map from EGK to the étale homotopy type of xk bar. And we should think of this as determining homotopy fixed point for the étale homotopy type of xk bar. The étale homotopy type of xk bar is canonically isomorphic to the étale homotopy type of xc. So this is a profinite completion of the C points. So what we would get by drawing a picture of the curve and taking its C points, this looks just like the profinite completion of those C points. So we think of phi prime as being in a mapping space from EGK to Étale homotopy type of xk bar fixed by gk, and we think of this as an appropriate notion of homotopy fixed points. So in total, the unwinding is that what we were denoting maps from the Étale homotopy type of spec k to the Étale homotopy type of x, in this case, are in bijection with the homotopy fixed points of the Étale homotopy type of xk bar. And that's because, again, this is hiding the triangle over there. This is hiding that all of these maps are occurring over the Étale homotopy type of spec k. So what we'd like to discuss is whether the k points are the same as this. So the section conjecture, which is right there, says that this is supposed to be the k points. And now, so thus the section conjecture says that we have a map from xk to this set, which we're now calling homotopy fixed points of the Étale homotopy type of xk bar here. And it says it's asking that this this is homotopy classes of maps. So I ought to have put a pi 0 there. So we could say that the section conjecture could be rephrased as saying that the k points are the homotopy fixed points of a Galois action on our old replacement for the c points of the variety. So this is like the picture from yesterday of saying the r points were the fixed points of the c points under the Galois action. Here, these maps of Étale homotopy types are the pi naught of the homotopy fixed points. So let's give the analogy to Sullivan's conjecture by recalling Sullivan's conjecture. So this is a theorem proved both by Haynes-Miller and Gunnar Carlson and Dwyer-Miller-Neisendorfer and Land. And it says that the homotopy fixed points for an action on a finite complex of a finite p group are the same as the fixed points after a p completion. So for x, finite CW complex, let's like G, finite p group, x, finite G CW complex, then we get a map from the fixed points of G Bausfield-Kahn completed at P to the homotopy fixed points of the Bausfield-Kahn completion of P, and that this is a weak equivalence. So in some cases, we've got something like an equivalence between fixed points and homotopy fixed points. We were looking at the section conjecture as saying that these maps of Étale homotopy types were the homotopy fixed points. The k points, they are the fixed points of the k bar points. K points are also discrete, so it would be sort of for free to add a pi naught there, because for k a number field, there are finitely many solutions in k to equations determining a hyperbolic curve. So what we have is that the section conjecture is analogous to an equivalence between fixed points and homotopy fixed points for Galois actions on hyperbolic curves. Oh my goodness. So I apologize. I really used my time badly. Let's So I think because I'm a tongue-tied enough speaker, I'm going to continue through with drawing an example of this map. So we have by functoriality this map from the section conjecture, but you can make it very explicit. For one thing, you could draw everything over R, and the next thing I had planned to draw is this picture over R. And let's go through until 2:15, and we won't finish the story, so I'll apologize now and make this explicit over R. So the Sullivan conjecture is for finite p groups. If K is R, then the Galois group of K is Z mod 2, so that's definitely a finite p group. So you could use ideas related to that to show section conjecture over R. The statement's a little bit different. So this this leads to a section conjecture over R, which is true and has several different proofs. And let's do an example of this. So last time we were considering the example y squared equals some polynomial in x with distinct roots. And let's let this be x minus 1 times x minus 2 times x minus 3 times x minus 4. So we can draw this. So here's our scheme x mapping down to the to c, to the x coordinate. So we could take xy mapping down to x. And again, this has two different values of y for each value of x, provided you're not at 1, 2, 3, or 4. And this is a branched covering space, but if we made slits such that you have to go in any loop around 2 branch points, it splits apart. So what we get would then be split like this. The gluing is the underslit to the overslit, so it looks complicated, so we're really going to flip this over. But then once we do that, we see that this is a torus missing 2 points. Let's actually make x. So we add 2 points and form x, which now looks like we have our two cylinder pieces like this, and then we fill in these with an extra 2 points at plus infinity and minus infinity. So we're going to investigate the fact that that this map is a bijection on pi naught. So it doesn't matter over R because it's Sullivan's conjecture. And note that we're going to stick a pi naught in there because we've got fixed points equivalent to homotopy fixed points. And so for genus greater than 2 and the number field, your solutions are discrete. Okay, so let's write down the map in the section conjecture. So we're looking at a map from x of r to the homotopy fixed points, really pi naught of the homotopy fixed points of the Galois action on xc. We should put a profinite completion in there, but we don't have to. And we're going to show that this map is a bijection after taking pi naught here. So the goal of this example is to see that we have a bijection between the real points of this curve and the homotopy fixed points of the C points. So what are the real points? Well, y squared is real whenever the right side is real and positive. So that happens when when x is very big, as in bigger than 4, then all of those things are positive. Happens when x is very small, and it happens in between those two slits. So on this picture, that's two different loops up here going out to the two different points at infinity. So there's one, and here there's the other. So the homotopy fixed points, since this is a k pi 1, you can convince yourself that pi naught of the homotopy fixed points is in bijection once you choose a base point, and I'll give the bijection since this is an example. So after choosing a base point, we can identify, so choose B base point in x of r, and after doing that, we get a bijection between the group cohomology of HGR with coefficients in pi 1 of xc. And here we have our real points. And the way this map is made explicit is that if we take a base point x in here, we send it to the element of group cohomology represented by the following cocycle. So element of group cohomology is determined by a cocycle, and we send G, an element of GR, to some element of pi 1. And here's the element of pi 1. So let's say our base point was here. And our point x was here. We can choose any path from b to x. And we'll call that gamma. Then we act the element g on it, so gx on the complex points. G is an element of the Galois group. And then gamma goes to something else. Maybe it goes to this. So that's g of gamma. And so this g gets sent to the path from b to itself, which goes g of gamma followed by gamma minus 1. And we can really compute that. So for instance, if we'd chosen the path, if we have b here and x here, and we choose the path like this, then gamma, it flips the x coordinate. So it's either something like this or something that goes around like that. If I did this right last night, it's g of gamma just goes around like that. And with more time, we could work this out all in all its transparent detail and see that pi 1 of xc, well, we know it's z plus z, and it's generated by a little loop that goes to its negative here and another loop z, so we could call that z plus z with the minus 1 action, and let's call that z plus z1. And then we would see that h1 gr of pi 1 xc is the Z2 cohomology with constant coefficients in Z for H1, that's 0. That's Z mod 2. So this would be a Z mod 2. You send the base point to 0. And the x on a different component to the non-identity element. So what we get is that the map x to r to h1 gr z plus z1 equals z mod 2 sends anything, it factors through pi naught, and it sends b, the base point, to 0. It sends x not in with base point to 1. So that's an example, and I think you'll have to take my word for it that it's something that can be entirely worked out. It can even be worked out over arbitrary fields for an elliptic curve. So for any field, K, in this example, the map from the section conjecture is the Kummer map from elliptic curves. So for any field K, this map, the map from X to K to the maps of étale homotopy types can be identified with the Kummer map of the elliptic curve. And this example is an elliptic curve whenever you have a K point. So we've just worked out a Kummer map over R. Okay, so for the analogy of between fixed points and homotopy fixed points, there's a way to rephrase the section conjecture in terms of fixed points and homotopy fixed points for a field K. There's a reference of Gary and Quick about doing that well. So the next topic that I planned for this talk is on limitations of the étale homotopy type as a tool for understanding schemes. And let me advertise them very quickly. So the first is the Selmer group from number theory shows that you can't have the points of an elliptic curve being the same as these maps of étale homotopy type because the Selmer group is actually smaller. So that makes the section conjecture fail off the bat. You could impose what fails, these local conditions, and then it becomes the same as, bless you, as having no infinitely divisible elements in the Tate-Schaffer-Ravitch group. So that connects up with the finiteness of Shaw. That's also a result of Isaacson, that the étale homotopy type can be sent through the category of A1 spaces in algebraic topology, in A1 algebraic topology, and this puts another set of morphisms, namely the morphisms of spaces, in between the two. And lastly, there's a nice result of Vygotsky saying that morphisms of certain morphisms of étale sites are the same as morphisms of schemes. And we were talking yesterday about how the étale homotopy type is the shape of the étale topos. Maps of sites are similar to maps of topoi. So Vygotsky's telling us that the maps of the topoi are picking up maps of schemes up to universal homeomorphism. So what the difference between that and having something like the section conjecture and indeed the Anabelian conjectures is then passing through the shape. So we don't have time to finish, but thank you very much.